My name is Kim Buckley, and I'm a member of the Science, Medicine, and Technology Subcommittee at HASP. And I'd like to welcome you to this morning's class presented by Peter Gonthier, and it's entitled The Fascinating World of Magnetars. And I'm very much looking forward to learning a little bit more about that because I know absolutely zero now. So by way of introduction, Peter Gonthier is a professor of physics at Hope College, where he's been teaching since 1983. He's also director of the Hope College affiliate of the Michigan Space Grant Consortium and a member of the American Astronomical Society, the High Energy Astrophysics Division. His areas of research interest include radio, X-ray, and gamma ray astrophysics, neutron stars, and pulsars. Peter received a BA in chemistry and a PhD in nuclear chemistry from Texas A&M, and he completed a postdoc fellowship at the Max Planck Institute in Heidelberg, Germany. He's also been a guest professor at the Physikalisches Institute in Gießen, Germany. So without further ado, I'll let Peter take over, and Peter also has a student working with him on this presentation, and I'll let Peter do that introduction. Peter, take it away.
Thank you, Kim. I would like to introduce Meredith Boomers. She's been doing research with me in this field of magnetars. This is her third summer. And she has done a great job, and we're working on a couple of papers at the moment and hope to have those submitted by the end of the summer. So we are here to share with you some information about magnetars. I would encourage you to ask questions. There is some thumbs up that you can click on to kind of alert to a question or so, and I can stop and we can try to answer as we go. I think it would be better to do that than wait till the end, but either way. The presentation, as you know me, is going to be technical. We start out with the dessert, and then things get complicated along the way. But hopefully I can keep you all in line. And so I'm gonna begin sharing my screen here. I'm just gonna share my desktop. Well, okay. I think I can just share my, so this is my PowerPoint, or it's actually a keynote on the fascinating world of magnetars. So what I would like to do is tell you about what are magnetars, some of the characteristics, introduce you to the pulsar zoo, talk a little bit about solar activity. It's the star that we know the best about how it works, how it functions. And then some activity of magnetars, which is similar to the activity that we find in the sun. And then I'll talk for about an hour, and then I would like to turn it over to Meredith to talk about the work that she's been doing specifically associated with the microphysics that we need to implement to be able to do some realistic simulations of what's happening in the magnetospheres of magnetars. And we'll try to have some time at the end for questions. So I can say that magnetars the name is basically coming from the idea that it's a highly magnetized star. It's a neutron star, so that's what characterizes a magnetar. And we could say, okay, that's it. But there's a lot more that we need to say about magnetars. So here's a nice cartoon that is coming up in a magazine on the origins of magnetars. And so they're neutron stars. And so we need to talk a little bit about neutron stars and what they are. The mass of a neutron star is about 1.5 solar masses. They tend to vary between 1.4 and I think the most massive neutron star is something like 2.2. And so recently there was a gravitational wave detection of a black hole and some other compact object, which seems to have an unusual mass of 2.5 solar masses. And so then it could be the lightest black hole or the most massive neutron star. And that's an interesting question that needs to be further understood with more events coming along our way. If we translate that to kilograms, of course, it's a huge number. I'll try to get my cursor on here. It seems to have disappeared. Where are you, Mr. Cursor? Okay, so the size of these stars are very small. Somewhere around 10 is the canonical radius that is quoted. There we go, there's my cursor. But nowadays, I think we talk more about 15, 16 kilometers in radius. So this is somewhere a star that is typically the size of a small city, and yet about a sun and a half in mass. So that leads to what are referred to as nuclear densities. That's of the order of 8 times 10 to the 8th. So this is like 800 million tons per cubic centimeter. So this is like a teaspoon. So this is basically the density of a nucleus of an atom. And the name neutron stars suggests that it's mostly neutrons, but obviously there's much more in a neutron star. There are very neutron-rich elements as you come toward the surface, which is a crust of some thickness, and then the inner part of the star circulates or rotates at a different speed than the outer part, and hence generates an enormous magnetic field. They typically rotate as fast as a couple of milliseconds. So at some point there is a rotational limit Otherwise, they start tearing apart. So it's believed to be about 1.5 milliseconds. And then some of these slow rotators are of the order of 23 seconds. So there's a wide range of rotational periods there. Magnetic fields are a broad range from 10 to the 8th to 10 to the 16 Gauss. So there are 8 orders of magnitude there. Astrophysicists like to use CGS units. The MKS unit of a magnetic field strength is a Tesla. So there's 10 to the 4 Gauss in a Tesla. So these are huge magnetic fields that we cannot reproduce here on Earth. And so these are very exotic laboratories for testing the theory of physics, which is known as quantum electrodynamics, which is the most successful theory in physics. So the magnetars are a group of high magnetic field neutron stars. So what are neutron stars? Would be the next question to try to deal with. Well, they're the remnants of what we call a high mass star, somewhere between 8 solar masses and 25 solar masses. Below 8 solar masses, the remnant winds up being a white dwarf, which is a star about the size of the Earth. Still very dense, maybe anywhere between half a solar mass and 1.4 solar masses. Beyond 25 solar masses, it is believed that the remnant that remains is a black hole. So there's a short life on the main sequence for these high mass stars. You would think that because it's a high mass star, there's plenty of fuel and therefore it should live longer than a low mass star, but it's the other way around. A high mass star is going to have the fusion taking place at very high temperatures, and therefore the reaction rates are much higher than low mass stars, and therefore they only live for somewhere between 4 and 20 million years, depending on the mass. And then, of course, once they move off the main sequence, they live a much shorter life, and they wind up fusing heavier elements off the main sequence, producing an iron core, and fusion occurs in shells. This is an illustration of a star reaching its end point. There's a core that is iron. This is the most stable element, and so fusion stops at iron. In shells, like an onion skin, there is fusion of silicon and sulfur and magnesium, neon, carbon, helium, and hydrogen. So then it's showing you a thin envelope that remains and the outer part of the star. So this is basically a star at which it's reached its endpoint. At that particular point, then the iron core collapses very quickly in a in a millisecond. And as it collapses, there is an explosion that takes place, which is known as a supernova explosion, and shatters the outer part of the star. It's a complicated process and one that we know fairly well, but there are still details that are not yet totally understood. The classic example that is in our night sky is the Crab Nebula. That is the remnant of a supernova that took place in 1054 AD, so that's about 1,000 years ago. And it is about 6,000 light years away from us. This is an image that is made from 4 different telescopes. It's a radio image along with an infrared image. So the radio is actually the Very Long Baseline Telescope. The infrared is from Spitzer. Then there's a Hubble Space Telescope image. And finally, the Chandra X-ray image, where you can see some toruses here. The neutron star that remains behind is kind of where my cursor's at. It is a pulsar. It is a neutron star that is rotating about 33 times a second. And it is not a magnetar. The magnetic field is not quite so strong, but it is emitting a beam of light that we happen to be in the pathway of that beam. And so then we see it pulse because of its rotation. We'll talk more about that in the next slide. So neutron stars radiate. And I want to illustrate what is called magnetic dipole radiation by this cartoon. This is a dipole antenna. Maybe some of you all have been ham radio operators, and you have built your ham radio or have built your antenna, and this is like a dipole antenna, which is basically a single element, aluminum element, and you basically pass an alternating voltage across the antenna so that you have an oscillating current going through, and you produce a magnetic field because there's a current going through, and then you have a magnetic field that is a time-varying magnetic field, and you require a time-varying magnetic field to produce electromagnetic radiation. So then you have a transmitter then that you can use this antenna to transmit your radio waves. And if you take a bar magnet and you rotate it, you obviously have a dipole magnetic field, and you have to incline the bar magnet with respect to the axis of rotation. So you have the magnetic moment pointing from south to north in a different direction than the rotational axis, which would be given by the use of your right hand, say grabbing the arrow and pointing your thumb in the direction of rotation. And so this configuration would give you a time-varying magnetic field. And therefore, in a vacuum, this object would radiate. And so in order to radiate, it requires energy. So the energy is coming from the available rotational energy. So if this is rotating and radiating, then it has to be slowing down. And so that's what these pulsars are going to be doing. They're created with a certain period, but then they naturally slow down because they're losing energy through various radiation mechanisms that are taking place. So we come to this interesting radiation pattern that is taking place here. So this is illustrating dipole radiation that is taking place, and it is going to have a certain geometry to the radiation. It has a certain directionality and a certain pattern to it. And so we can calculate a rotational energy, which is known as, in terms of neutron stars, we say it's the spin down luminosity. So this is the available energy to produce radiation in one form or another. So it's basically 1/2 the moment of inertia times the angular velocity squared, or this can be written in this way in terms of its period. The magnetic field then associated with the spinning down, so how it slows down gives you some idea of the strength of the magnetic field. So if you can measure the period and you can measure how the period is changing, this P dot, or the period derivative, the rate at which the period is changing. So if it is slowing down, then there's a period derivative that is positive, and you infer then the magnetic field of the dipole associated with this neutron star in this fashion. So it's not that we go there and somehow measure the strength of the magnetic field. It's inferred through this relationship associated with the energy loss of a dipole magnet. So this is the polar surface strength of the magnetic field. That's the magnetic field at the pole at the surface of the neutron star. So we have here another cartoon illustrating the dipole field. So this is the north magnetic pole and the south magnetic pole. And the magnetic fields, because of its shape, and if there is radiation coming near the surface, it is collimated by the magnetic field structure, particularly with the radiation in the radio wavelengths. The radiation is collimated along the poles. So there is typically a central beam and an outer conal beam associated with the radio emission, and sometimes very complicated structures to that. The surface of the neutron star is very hot. The surface overall is hot, about 1,000,000 Kelvin to several million, depending on the age of the neutron star. But the poles tend to be hotter at the surface. And that's because you have charged particles that are trapped in the magnetic field, traveling along these field lines, either outward or inward. And those traveling inward are going to crash into the surface, heating the surface even higher than it is normally. And so you wind up with hot spots on the poles. The hotter it is, then the black body radiation associated with these hot spots are going to indicate a hotter temperature than the rest of the star. Because it's so hot, the black body radiation is coming out in the form of soft X-rays. These are low energy X-rays or lower frequency X-rays. And they have a certain very specific black body characteristic to them. And we can see the two different black bodies, if you wish, associated with the poles and the rest of the star. Then there's other mechanisms that can take place because you have this soft X-ray background that is emitting these photons from the surface. These soft X-ray photons can interact with charged particles that are being accelerated in the magnetosphere. And you can have a process that is referred to as inverse Compton scattering, where these soft X-rays scatter with relativistic particles. And mainly they're going to be relativistic electrons and anti-electrons known as positrons. And so these soft X-rays then get boosted to higher energies. And so then you see a hard X-ray portion in the spectrum associated with this mechanism. And this is characteristic of magnetars. And we'll see that as we go. So we talked about the collimation for radio emission. The highest energies in the form of gamma rays produce in pulsars. Now the interesting thing is that magnetars don't produce high energy photons in the form of gamma rays, but other neutron stars or normal pulsars do indeed produce gamma rays. So there's an interesting difference as to why there are no gamma rays coming from these highly magnetic field magnetars, but lower magnetic field pulsars produce even higher energy photons. And so one of the things that we proposed back in the mid-90s is that the photons in such strong magnetic fields can split into a pair of photons. So you might have gamma rays produced, but they split And this is a process that would be allowed by quantum electrodynamics and allowed only in very strong magnetic fields. But it's hard to prove or hard to test that theoretically at this point. But maybe in future, with future telescopes that will have a polarization sensitivity and be able to measure the polarization of the X-rays, that we might be able to have a better understanding of that. But the gamma rays nowadays seem to be coming from a region, an equatorial region that is outside fairly distant from the surface. So this is some contour lines which represent the magnetic field. This is, the axis here is along the magnetic field direction. And so this is the equatorial region. And this is showing you a theoretical calculation at different times when the magnetosphere when charged particles are introduced into the magnetosphere, and this is the current then that is coming back into the inner portion of the magnetosphere. And this is the equatorial region. So this is referred to as the current sheet, the equatorial current sheet, and this is where the gamma rays are being produced. And the theoretical work then show that these plasmoids form and detach themselves. And these plasmoids are going to be bundles of charge and high densities, and can lead to significant flares, if you wish, that are produced by these magnetic fields. And we see this phenomena taking place in the sun as well. And so it's of no surprise that we see this kind of phenomenon. Perhaps not the equatorial current sheet in the sun, because the strength of the magnetic field in the sun is not quite so high. So we come to this pulsar zoo. I just want to rearrange the images of each of us here. So these are pulsars. And what is plotted here is the period derivative. So this is the P dot that is measured, that can be measured. And this is the period along this x-axis. So these are two quantities that can be measured. If the beam of radiation happens to be in our way, then we see a lighthouse type phenomena where we see the star blink or pulsate because of the collimation of the radiation and the fact that the neutron star is rotating. Then we can easily measure the light curve and therefore be able to determine the period with time. And sometimes it requires lots of time in order to determine its period derivative. You see, this is the period, and this is the rate at which the period is changing. So this is 10 to the minus 21, a very small number compared to, say, the period of a few milliseconds here. So some of these pulsars might require years to determine the period derivative. And it's complicated because these neutron stars also twinkle in the atmosphere. And so you have to worry about the noise associated with the twinkling and how that has to be removed from the observations. So there's a whole family of interesting characters in this zoo. The most abundant species are these little blue dots, which are known as radio pulsars. These are also isolated neutron stars. That is a star by itself. You see these stars with circles in them. The circle indicates that it's a binary star system where you have the neutron star and some companion. And so these exist in binaries. You see some binaries in here. There's a few, but most of them are down here in a different group known as the millisecond pulsars, because their periods are in milliseconds. There's a group here with big squares on them, indicating that these have been identified as gamma ray pulsars by the Fermi Space Gamma Ray Telescope that's in orbit currently, and it's been in orbit for 13 years now. There are these green objects that are X-ray pulsars, seen to pulsate in X-rays. Then we also see that there are these dashed lines. These dashed lines are indicating the magnetic field strength. We showed that the magnetic field was proportional to the square root of the period times the period derivative earlier. And so that leads to a line slanted of constant magnetic fields. And these are different magnetic field strengths. So as we move up to the upper right-hand corner here, we increase in the strength of the magnetic field. So we have 10 to the 15, and then 10 to the 16 would be a little bit off the chart here. These red hourglasses are the Magnetar family. And so we have magnetars that are the highest field, but we have a magnetar that's a low field magnetar down here. It behaves as a magnetar, but it has a low field. So there must be an interesting connection between high magnetic field pulsars and the magnetars. But this is still something that is not yet totally understood. Off into this low period we have these millisecond pulsars. So presumably the idea is that these neutron stars are born somewhere up here and then are decaying because they're slowing down, and so their periods are getting longer. Eventually they stop being radio pulsars. If they're in a binary system with a close companion, and the companion turns into a red giant or a super red giant, then the neutron star can accrete material from the companion and spin up. And so the pulsar is then reborn with a short period as a millisecond pulsar. But perhaps at once they were over here as these other binary pulsars are also in this group. Then there's some other interesting critters such as radio transients that behave like pulsars for a brief moment and then shut off. And then there's other objects that are not emitting radio emission. And it could be just that we see them in other frequencies, but the radio beam is not in our path. And so this magnetar consists of two groups that were previously known as soft gamma ray repeaters, and another group of anomalous X-ray pulsars. And we'll see more details about those as we go. So that's the pulsar zoom. Basically, there are three main groups: the millisecond pulsars, the magnetic fields ranging from 10 to the 8th to 10 to the 10th Gauss. Then there are normal isolated pulsars between 10 to the 10th, 10 to the 14 Gauss. And then there are magnetars from 10 to the 14 to 10 to the 16 Gauss, the highest fields in the universe, probably. So, field strength. Here we compare the field strengths of other things in the universe and on the Earth. The field strength of the Earth is about half a Gauss on the surface, varies a little bit with latitude. The sun on the surface is about a Gauss. Jupiter has a strong magnetic field of about 6 Gausses on the surface again. Here's a Hubble image of Jupiter showing the aurora taking place in the northern pole of Jupiter. So these are a stream of charged particles coming from the sun that get trapped in Jupiter's magnetic field and follow the field lines down to the surface and excite the ionize the upper surface of the atmosphere of Jupiter, and you see it glow nicely. We have an example here of some sunspots. You see them as black because they are cooler, and there's such a strong contrast with the rest of the sun that they show up as black. There's a dark the umbra and the outer, less dark penumbra. And these are stronger magnetic field-wise. There's about 1,500 Gauss. So you go from 1 Gauss to 1,500 Gauss. So the field strength is much stronger here. And we'll see some of the interesting solar phenomena. Then we come to, I'm sure some of you all may have had an MRI done where you are inside of a very strong magnet. It's about 3 times 10 to the 4th Gauss, about 3 Tesla. The highest fields here on Earth are achieved in the high magnetic field laboratory, which is about 10 to the 6th Gauss. So we are approaching the magnetic fields of millisecond pulsars here, which begin at 10 to the 8th, but are not quite there. But you see, in order to get to magnetar field strengths, we got to increase the magnetic field by 9 orders. And so nowhere do we experience this kind of magnetic field strengths except near the surface of magnetars. This cartoon here is an interesting theoretical simulation of the magnetic field shape of the Earth. The different colors are the different polarities of the magnetic fields. We have field lines coming in to the North Pole. So we have a south magnetic pole and the north physical pole. And the north magnetic pole is in the south physical pole at the moment. It is known to reverse itself erratically every maybe 100 million years or so. On the other hand, the sun reverses its polarity every 11 years. So that's the solar cycle. And it is also associated with the sunspot cycle. There's interesting prominences. Here we have a nice prominence. There are solar flares, like here we have a prominence that has become unstable and has resulted in a solar flare. And then we have more violent activity known as coronal mass ejections, where a large energetic portion of the sun is ejected. And these can come our way, and it takes about 3 days to get to us, and can produce interference in satellites and produce the aurora for us. Here is a plot of the sunspot cycle. The amplitude varies, but it's a rather consistent cycle. Here's a nice prominence taken by a satellite known as TRACE, I believe. What we find is that the sunspots come in pairs and are typically connected to each other. The pair is connected through these flux tubes. And so you have these magnetic flux tubes that somehow are able to accelerate charge within these flux tubes. The surface of the sun is about 6,000 Kelvin, but the inside of these flux tubes, you can reach temperatures of 1,000,000. There's a nice link here to the Solar Dynamics Observatory, which I'll briefly go to that. You can see the sun as it currently is in many different frequencies, from visible to the ultraviolet or extreme ultraviolet. And we come over here to more lower frequencies. This is an interesting one because it's a magnetogram. So it's looking at a particular separation due to the magnetic field strength of the surface of a particular line, emission line or an absorption line, that there's a physics effect known as the Zeeman effect, that the splitting of that line measures the field strength. And so this gives you an idea of what the strength is. And then we have the overall intensity. So this is the Solar Dynamics Observatory that is in a geosynchronous orbit. Here they tell you where it's at and what it's doing. And the idea is to observe the sun constantly. And let's see if I can get back. There we go. So this is a little clip from the Solar Dynamics Observatory of a prominence. It comes from a YouTube video that is called Solar Rain. It's in 4K, so it's a very high resolution video, and showing this amazing sort of activity. And this is going on between two sunspots here, and you see some other that wants to form in various other places. So it's really an exciting place, very active. So this is a flare that is being recorded here, that is produced by this sunspot activity. And you have this flux tube that is pinched, and you have this magnetic reconnection that takes place. And so now you're borrowing a significant amount of energy from the magnetic field. So a lot of the energy comes from the magnetic field. And so magnetars do the same sort of thing. There are several types of bursts or flares. There's a short, that is in duration, bursts that can be in X-rays or gamma rays. They're brighter X-ray pulsars that pulsate, and therefore you can measure a nice light curve. These are these anomalous X-ray pulsars. The gamma ray repeaters are these short or long bursts of gamma rays. This is the other group of magnetars that show very strong magnetic fields. Then there's also transient events which just come and go. And then there is an interesting set of events that have recently been discovered known as fast radio bursts, which may turn out to be magnetars. And this is a spectrum from a magnetar showing the soft X-ray black body, and then you have this hard energy tail, and it extends some upper limits in gamma rays, and we'll talk more about that in this slide here. So we have this soft thermal background of photons coming from the surface. And then we all of a sudden have this hard X-ray tail that this is a power spectrum, so it's going up, but it has to come back down at some point. And the interesting thing is that the telescopes end their sensitivity at this point. And we don't have a telescope that is able to provide a continuation here for us at the moment. So these are future telescopes. Fermi is way over here. In terms of Fermi lat, the burst detectors on Fermi do come down to lower energy and do provide some magnetar observations for us that will be coming up in future publications. So it is believed that these high energy tails are coming from this Compton upscattering mechanism, where you have these soft photons scattering off of relativistic particles and being bumped up to higher energies. These are occurring near the surface, so it's going to be a very strong magnetic field. And in order to describe this mechanism, we need to use the results of quantum electrodynamics. And this problem was solved in 1986, in part by my colleague Alice Harding at Goddard's, NASA Goddard Space Flight Center, and another group. But we've been trying to develop these simpler analytics for the astrophysics community to use the results to characterize their simulations in a more realistic fashion of magnetars. And so that's what Meredith will be sharing shortly. We have bursts, short flares, and bursts occurring in magnetars. We have magnetars with some with short rotational periods, all the way up to 23 seconds or so. There's glitches, there's timing noise to things. And you can also see faintly magnetars in infrared and optical. And there's also transient pulses coming from them. In this graph here, I'm showing the inferred X-ray luminosity. That is the energy coming out in X-rays of magnetars and some pulsars. Sorry, this is a rotational. This is the spin down. This is the available energy, if you wish, in rotation. And we said that the energy must come from somewhere. And mainly it comes from this rotational energy. And this is the X-ray emission that is integrated and overall what is called the quiescent. Oh, this is a non-flaring X-ray emission. And this line is the line where you have the X-ray luminosity being equal to the rotational luminosity. So if you go here, you have 1, and it's 1 over here. And you come over here to 100, and you have 100 over here. So these magnetars are producing more energy in X-rays than is available in rotational energy. And that's what blows everybody's mind. These are X-ray pulsars that pulsate in X-rays. And as expected, their X-ray luminosity is less than the spin down. These are radio emitting magnetars, and their X-ray luminosity is slightly less than is available in spin down. So the question is, where do these magnetars get their energy from to produce so much energy in X-rays? And the idea is that it comes from the magnetic field. And this is the reconnection in these flares and the activity that must take place. And so the physics gets much more complicated to be able to explain these guys. And so that's what we would like to be able to simulate. But for that, we need to develop the realistic microphysics that is required to do so. And so what I'm going to do now is turn it over to Meredith, and let Meredith fill you in on some of the activity that we're doing at Hope College. We can answer questions along the way or wait until the end. She will have about 15, 20 minutes, and then we'll have a few minutes at the end. So Meredith, take it away.
Wonderful. Thank you, Dr. Gonthier. So as Dr. Gonthier mentioned, my name is Meredith Bomers, and I have been working with Dr. Gonthier on this project this is my 3rd year. And so I am very excited to talk to you guys about what I am doing with our research. So I'm going to quickly share my screen for you. Perfect. You should all be able to see it now. So before I begin, I want to take just a moment to thank our collaborators and everyone who has helped me and our research project along the way. So first and foremost is my mentor, Dr. Peter Gonthier. Without him, I wouldn't be able to do this, as well as our collaborators both at Rice University and NASA's Goddard Space Flight Center. There's Matthew Baring, Alice Harding, and Zorwar Wadia Singh. Our research is also heavily influenced by the findings of NASA's X-ray telescopes, Chandra and NuSTAR. And we are eagerly anticipating the launch of NASA's X-ray polarimeter, IXPE, at the end of this year, and the significance that it promises to hold both for our research and the field at large. So Dr. Gonthier has already introduced you to the subject of our research, magnetars. I'm going to pick up where he left off, tell you a little bit more about their strong magnetic fields, as well as a subatomic process called Compton scattering that occurs within those fields. That's what our research is focusing on, so I will explain our research to you in that context and talk to you a little bit about some of the hopes we have regarding where our research is going to be taking us in the future. So, what are magnetars? Magnetars, as Dr. Gonthier has mentioned, are highly magnetized subsets of the neutron star population. They are characterized by their high energy electromagnetic radiation that they emit. There are two types of radiation, gamma rays and X-rays. And based on the type of radiation, magnetars are divided into two categories: soft gamma ray repeaters and anomalous X-ray pulsars. So as you can see here, as the magnetic field of a magnetar decays, that's when they're emitting this high energy radiation. And the radiation that's being emitted is energetically excited via Compton scattering, the process that we are studying, into the high energy hard X-ray tails that you see here above the 10 keV line. So in the magnetic field of a magnetar, those magnetic fields are typically around 10 to the 14, 10 to the 15 Gauss. And this number is above the quantum critical value of 4.41 times 10 to the 13 Gauss. So what that means for us is that when we are looking at Compton scattering and other processes that happen within those magnetic fields, we have to be using quantum electrodynamic treatment. And so that comes with a bunch of different properties for the electrons and photons that I'll get to in just a second. But I think along the way, there was a question about magnetars and their size with respect to the Earth. So when you're looking at a magnetar, the diameter of the magnetar is typically around 20 kilometers. We can compare that to the 12 to 30, or just under 13,000 kilometers that is the diameter of the Earth. Now, interestingly, Dr. Gonthier mentioned that magnetars are very, very densely packed. So the mass of a magnetar is about 1 to 2 times the mass of the sun, and all of that mass is packed into such a small size, such a small diameter, which means that if you were to take about a tablespoon of a magnetar, that tablespoon would end up weighing over 100 million tons. So that's how dense and how small those magnetars are compared to the Earth. So again, when we're looking at the magnetic fields of the magnetars, we're using quantum electrodynamic treatment when we're dealing with Compton scattering, the process that we're studying. So what that means is that we have electrons and photons involved in this interaction. And electrons have two main properties that we care about. One is their spin. An electron can either be spin up or spin down. And that's just a way that we use to categorize them. It's an inherent property of the electron, just like its energy is. And then they also have that energy or an energy level. So electrons can't have just any number, any size of energy. It has to exist at concrete Landau states. So there's just distinct energy levels that an electron can exist in. And in Compton scattering, we have an electron that exists in 3 distinct states. So there's an initial state, an intermediate state, and a final state to the electron. In each of those 3 states, the electron has unique spin and energy level properties. So the other particle that's involved in Compton scattering is the photon. And the photon has a property called polarization. And polarization refers to the orientation of the photon with respect to the magnetic field or the plane of the magnetic field. So a photon can either be perpendicular or parallel to the magnetic field, and that's what we refer to as its polarization. In Compton scattering, there are 2 photons involved. There's an incoming photon and a scattered final photon. And each of those photons can have its own polarization. So what is Compton scattering? Well, Compton scattering occurs when you have a relativistically moving charged particle. So here we are looking at the rest frame of the electron. So we're taking Compton scattering from the perspective of the electron. So we're going to say the electron is at rest, and there's an incoming photon that comes in and collides with and is absorbed by the electron. So that photon energetically excites the initial electron into the intermediate middle virtual state. So that's a higher energy level. And then from there, the electron emits that final photon and is accordingly dropped down to its final state. And there's two orientations or ways that this can look, and these are depicted here by the two Feynman diagrams that I have. So this equation that you see is what we call the differential Compton scattering cross-section. And the cross-section is essentially the probability that an electron and a photon are going to interact via Compton scattering and not some other process. And I'm going to skip over most of the terms in this equation, but I do want to draw your attention to these z terms that you see. And as you can see, these z terms are denoted by either a subscript of 1 or 2. That refers to the two Feynman diagrams or ways that Compton scattering can occur. So as you can see, the differential cross-section takes into account both of those Feynman diagrams in combination. So some of the goals for our research are to create a concise, fully spin-dependent expression for Compton scattering that we can use to produce accurate numerics via via Monte Carlo simulations. Over the last few years, we have worked with a similar process called cyclotron emission, which is similar to Compton scattering, but a little bit simpler. And we've had good success in reducing that and creating a complete general expression for cyclotron emission. So we've been using the tools that we accrued along the way with that endeavor as we seek to simplify and make a fully spin-dependent expression for Compton scattering. Now, previous literature does have expressions for Compton scattering out, but all of those have various simplifications or are only dealing with a specific case. For example, they might be taking the sum or average of spin states of the electrons, or perhaps only dealing with the case where the final electron scatters down to the ground state. So the goal of our research is to create an expression that is completely dependent on spin of the electron, photon polarization, incoming and scattering angles, and just have all of those variables in one concise expression. So I mentioned that we want to incorporate spin dependence of the electron, and I'm going to use this graph to illustrate to you why that's so important to us. So what we have here is on the y-axis, we have the electron energy widths plotted as a function of the magnetic field in units of the critical magnetic field. So this is for the specific case where the initial electron starts at an energy level of 1 and ends up at a final energy level at the ground state. And you can see the three different lines here represent, for blue, the spin down case where that initial electron is spin down. For green, it's the initial electron being spin up. And the red is the spin average. And for the specific case, as I said, the final electron is in the ground state. At the ground state, an electron can only be spin down, so that's not a variable in this graph. And what I'd like you to point out is that at higher magnetic fields, well above the critical value, all of the lines tend to converge. So there's not that much dependence on spin or variability that comes with spin for the energy widths. But at right around the critical magnetic field, as well as below, there's a great deal of dependence on width or on spin and changes that come from it. So as I mentioned, previous literature has used the spin average, so following this red line, rather than having variables in their expressions which can account for whether the initial electron is spin down or spin up. So to illustrate this in a different way, again, emphasizing the reason for including spin dependence in our equations, here we have those energy widths that we looked at in the previous graph, but taken as a ratio. So this is the spin down energy width over the spin up energy width. So obviously, as that ratio approaches 1, those widths are the same, so there's not that much dependence on spin. And the further that ratio is away from 1, so going into the red color, the more dependence on spin there is. So this graph is a plot of we have the magnetic field on the y-axis as a logarithm, and we have the initial energy levels on the x-axis. And so as you can see, here a magnetic field equal to the critical magnetic field, or 1, is the 0 on this axis, since we're looking at the logarithm. So as you can see, at lower initial energy levels, there is much more dependence on spin. So we're further away from the purple, more towards the red at those lower energy levels. And across all energy levels, you can see that there's the most spin dependence right around the critical magnetic field, as well as slightly below. And no matter what energy level you're looking at, if we were to isolate just one of them and look at it as a cross section, you can see that there's kind of a hill-shaped pattern to it going up. So we start out at low, very low magnetic fields near a ratio of 1, so there's not a lot of spin dependence. As we go up towards the critical magnetic field, there's much more spin dependence. That ratio is going away from 1. And then as you pass the critical magnetic field and go above it, the ratio approaches 1 again. So we can see that even more clearly here. So again, on the y-axis, here we have the ratio of total widths. So again, as that's 1, there's much less dependence on spin. Those widths are essentially the same. And the further away from 1 it goes, there's much more dependence on spin. This graph is isolating several initial energy levels for that initial electron. And just like we saw in the previous graph, at lower initial energy levels, there is much more dependence on spin. So looking at the case where n equals 2, the ratio of total widths is the furthest from 1. So there's the most spin dependence in that case, decreasing as we go up to an energy level of 100 here at the bottom. And again, as we saw in the previous figure, the dependence on spin is the highest near and slightly below the critical magnetic field. So again, that's what we saw on the other graph. And this just goes to emphasize the reasoning behind including spin dependence in our equations and why we want to incorporate those. So the other property that I mentioned that we want to include in our expressions is that of photon polarization. Now again, photon polarization is the orientation of a photon with respect to the magnetic field. Again, in Compton scattering, there are 2 photons involved. There's an incoming photon that's absorbed by the initial electron, and there's a final photon that is emitted by the electron. Each of those can have its own polarization, which gives us 4 combinations of photon polarization. The initial and final photon can have the same polarization. They can have opposite polarizations. So that's where we get the perpendicular to perpendicular initial and final, parallel to parallel, or different combinations of the 2. So this graph is looking at that differential cross-section. So again, the differential cross-section is essentially the probability that an electron and a photon are going to be interacting via Compton scattering and not via some other interaction. And this is plotted as a function of the final angle or the scattering angle where that final photon is emitted. Here we have several of our variables fixed. So we have a magnetic field equal to the critical magnetic field. We are scattering down to the ground state for that final electron. Again, that means that the final electron has to be spin down. We have a fixed incoming angle. And what we can note here is that for this specific case, there is a preference, so a higher cross-section or a higher probability for the blue line and the green line. So here there's a preference for the 2 cases where the final photon has a perpendicular polarization. And this can be different in different cases, but for this specific instance, there is a difference, there's a disparity in values of the cross-section based on the polarization values of the photon. So that again just goes to emphasize why we are intentional about incorporating photon polarization into our Compton scattering equations or expressions, and why we want to have those variables spin dependence and photon polarization involved in our expressions. So again, the goals of our research is to create those concise, correct spin, photon polarization, angle of incidence and scattering dependent expressions for general Compton scattering. And we're hoping to use those expressions in applying them in Monte Carlo simulations so that we can achieve accurate numerics of Compton scattering. And we're hoping that this research will be able to assist both current and future NASA missions as they seek to explore more about X and gamma rays, as well as particularly with IXPE, the new X-ray polarimeter set to launch at the end of this year, as it seeks to learn more about photon polarization effects. So with that, I would like to thank my mentor, Dr. Peter Gonthier, for his help and allowing me to work on this project. I'd like to thank the rest of the Hope College Astrophysics group, both current and past, as well as our collaborators at Rice University and Goddard Space Flight Center, as well as Goddard Space Flight Center for hosting us on multiple occasions. And I'd also like to thank all of you for listening and open up to any questions.
I have several questions. I'd like to go back a bit in the presentation and have a better understanding of what the quantum critical value is. What does it represent? What is the significance of that value?
Yes, so the quantum critical value here is 4.41 times 10 to the 13 Gauss. And that value is essentially the threshold that we use to determine whether or not we are going to be treating the processes that happen in the magnetosphere, in the magnetic field, with quantum electrodynamic treatment or classical treatment that we have like here on Earth.
And this is because, to put it bluntly, the rules of physics change at that threshold?
I'm going to allow Dr. Gonthier to continue.
You've answered this before. Basically, nothing magic happens at this particular point. This field is defined by the fact that an electron in the magnetic field will have an energy that is known as the cyclotron energy that is equal to the rest mass energy of the electron. And that occurs at a field strength of this quantum critical value. We don't anticipate anything drastic to happen above or below this field. These fields are already very strong and a lot of different physics that would not normally occur because of quantum electrodynamics. New physics basically does indeed open up in these high field strengths. I hope that helps. If not, let me try again.
It does help. As you said, it's not a magical number. So
Yeah.
Where does the traditional method fail at this point?
Well, it fails. Basically, Compton scattering is treated in different fashions. Normally, a textbook treatment of Compton scattering will treat this non-relativistically. So you need to include special relativity, but then it could also be non-relativistic because you are not including the magnetic field. So in order to include the effects of the magnetic field, then it needs to be done in this quantum electrodynamic fashion where the field actually participates. And you put the Feynman diagram up for me. So what happens here is that the photon is in essence is absorbed, you might say, by the electron. And there's this virtual state. It's called a virtual state because we never really see it. But this virtual state all of a sudden can be anything. Anything in the sense that it's an electron coming in, but the virtual state could be a positron, an anti-electron. There are different possible states for this virtual state as an electron, as a positron. It can exist in any excited state, any Landau state, because the perpendicular momentum is not conserved in this case, and it borrows energy from the magnetic field momentarily within the Heisenberg uncertainty. And so the energy width reflects basically the lifetime of this state. The lifetime, how long the state lives, is inversely proportional, if you wish, to what Meredith referred to as the energy width. But then out comes the electron again, and it's going to be a different photon that shows up in the final state. And so the only way to treat this type of physics is to do so within what is referred to as quantum electrodynamics, because it's the scattering of light with a charged particle.
Okay, that helps. Thank you. If there's no one else, I'm still confused by the concept of a width in this particular case.
Yes.
Does it equate in very fundamental terms to what we might refer to as bandwidth, meaning a range of frequencies or energy levels? There was a reference to spin-dependent width. This is a new concept for me.
Yes. Can you put the levels that you had there? Yeah, so these are supposed to represent the excited states of, say, that virtual state. So these are different quantized states, different values of n. So n is equal to 0. This is the ground state. And then you have these excited states, n equals to 1, 2, and so forth. This is how much energy the electron, how much perpendicular energy the electron has in this virtual state. So there's also parallel energy, but that is actually conserved, or parallel momentum, but it's this perpendicular quantity that is not conserved. These states are not infinitely well defined. There is a thickness to that state, if you wish. because there's a lifetime to it. This state exists for a very short period of time, and therefore Heisenberg uncertainty principle tells us there must be a corresponding energy width to it. And this is true for all quantized states, for the electron in a hydrogen atom, say, as it is excited, it has to decay to the back from that state. Because it decays from that state, it will have an energy width that is related to its half-life form. And so you can either talk about the half-life or you can talk about the width. And that's what is being referred to basically. If you looked at the photon coming from this excited state, from the top excited state there, you could see that you would get a discrete energy of the photon. Not really, because it would be smeared because of that energy width. Your detector has to be very, very good to be able to measure that smear, but oftentimes the resolution of the detector is better, and so you can actually measure the lifetime of some of these states in this fashion. The idea that it's spin dependent is that the lifetime of that state depends whether the spin is oriented along the magnetic field or in the opposite direction against the magnetic field. And QED tells us that there is a lifetime dependence to that. And this is something that is usually ignored by people doing these simulations, because it's much harder to do the simulations taking this into account. There isn't in the literature a very nice description of these details that would allow someone to take the equations and program them into a computer program. This is what we hope to supply.
Okay. Thank you.
Mm-hmm. And we're happy to answer more questions. We're not in a rush. We're here.
Okay, I guess we have a question. We were wondering, how do you measure the magnetic field of an object that's thousands of light years away? What's the secret?
Yes. May I have the screen sharing back? Thank you. Let's see. It's going to be inferred. I listed this equation that comes out of this idea that a spinning dipole radiates and therefore loses energy, which means that it has to slow down. Because a neutron star is slowing down, it's going to display a positive period derivative, or a positive rate of change of the period. And so the strength of the magnetic field then is going to be proportional to how fast it is slowing down, you can envision that a stronger dipole is going to slow down faster because it radiates faster or more energy. And the dependence is such that it's proportional to the square root of the period and the period derivative. So that, assuming that the magnetic field of the neutron star is an electric dipole, is a magnetic dipole, if you have measured the period and the period derivative, then you can infer the magnetic field strength. And so that is the way that typically the magnetic field associated with pulsars is measured. It's really inferred.
So obviously then you have to have the rate of decay has to be fast enough that you can get some pretty good measurements relative to what you're trying to calculate. So just can you give us a sense of how long these things take to decay, and what kind of a change can you observe over a year? Maybe decay is not the right word, but the slowdown, spin down.
Yes.